The video editor at the post-production house in Burbank noticed the port was gone on a Tuesday morning in January 2009. He had been editing professional video since 1998. For 11 of those years, the FireWire port on his editing workstation had been as fundamental to his work as the keyboard and the monitor, the connection through which raw video traveled from camera to hard drive to editing software, fast and reliable, and invisible in the way that essential infrastructure is invisible until it fails or disappears. The new MacBook Pro that the facility had purchased to replace his aging workstation did not have a FireWire 800 port. It had USB 2.0 ports and a single FireWire 400 port, the older, slower standard that the professional video community had largely moved past by 2005. His professional video camera, his external hard drives, his audio interface, all of them connected through FireWire 800. None of them would connect to the new machine without adapters that degraded performance. He called the facility's technical director, who called Apple's enterprise sales line, who explained that the new MacBook Pro line had been redesigned to emphasize portability and that the FireWire 800 port had been eliminated as part of the reduction in port count that the new design required. The technical director thanked the Apple representative and spent the rest of the morning on the phone with their hardware vendor discussing whether the new machines could be returned. They could not. The facility spent approximately $14,000 over the following month replacing FireWire peripherals with USB 2.0 and eSATA equivalents, upgrading firmware, and in several cases replacing equipment that had no USB equivalent with newer models. The $14,000 was not the largest unplanned expense the facility had absorbed. It was the most frustrating because it was unnecessary. The technology being replaced was faster, more capable, and better suited to professional video work than the technology replacing it. The video editor, whose name was Marcus Webb and who had been editing professionally since before FireWire existed, described the experience to a colleague with a precision that captured something important about how technological standards actually change. He said, "The better technology lost." America in the mid-1990s had a connection problem that most consumers did not know they had because the problem was so thoroughly embedded in their experience of personal computing that they had never imagined it being different. Connecting a peripheral device to a personal computer in 1994 was an exercise in frustration that required technical knowledge, patience, and occasionally a screwdriver. The parallel port on the back of an IBM-compatible PC, the wide, flat connector that printers used, communicated at approximately 150 kilobits per second. The serial port, the narrow connector that modems and some other peripherals used, communicated at approximately 115 kilobits per second. Both required the computer to be turned off before connecting or disconnecting a device. Both required configuration settings, IRQ assignments, DMA channels, port addresses that conflicted with each other in ways that were difficult to diagnose and frequently impossible to resolve without expert assistance. The Apple Macintosh was somewhat better. The SCSI port that Apple had included since the original 1984 Mac allowed connection of multiple devices in a chain and communicated at up to 5 megabits per second. But SCSI required careful attention to device IDs, termination, and cable length, and the consequences of getting any of these wrong ranged from devices not functioning to data corruption. These were the connection options available in 1994 to the owner of a personal computer who wanted to add a scanner, an external hard drive, a digital camera, or any other peripheral device. The experience was uniformly poor. The performance was uniformly inadequate for the emerging generation of devices that would need to transfer large amounts of data, digital video cameras, high-resolution scanners, external storage. Two organizations were working on this problem simultaneously, from different directions and with different priorities, and the solutions they produced were both technically excellent and fundamentally incompatible in their commercial philosophies. One was Apple Computer, working with Sony, with the IEEE standards body, and eventually with Texas Instruments on what would become FireWire, formerly IEEE 1394, named for the standards committee that ratified it. The other was a consortium of personal computer companies, including Intel, Microsoft, Compaq, IBM, DEC, and NEC, working on what would become USB, Universal Serial Bus. The technical work from both groups was genuine. The commercial interests embedded in each project were the forces that would determine the outcome. The FireWire standard had its origins in Apple in the late 1980s, where a team of engineers led by Mike Tiener was developing a high-speed serial interface for professional audio and video applications. The driving requirement was bandwidth. The digital video formats being developed in the early 1990s, specifically the DV format that Sony and other consumer electronics manufacturers were developing for digital camcorders, required data transfer rates of approximately 25 megabits per second to transfer video in real time. The storage formats being developed for high-resolution audio and for professional video editing required even higher rates. No existing consumer computer interface came close to these requirements. SCSI could theoretically reach the required speeds, but was too complex and expensive for consumer devices. The emerging IDE interface, used for internal hard drives, was not designed for external connection. Nothing available in 1990 could do what the next generation of digital media devices was going to need. Tiener's team designed FireWire from first principles to address this gap. The standard that emerged from this design work was technically ambitious in several specific ways. The data rate was high. The initial FireWire standard specified 400 megabits per second, 16 times faster than the fastest SCSI interface available when the work began. The later FireWire 800 standard doubled this to 800 megabits per second, and FireWire 3200, which was ratified but never achieved mass market adoption, specified 3.2 gigabits per second. The connection was isochronous. The standard guaranteed that data would be delivered at a consistent rate rather than in bursts, which was essential for real-time audio and video applications where irregular data delivery caused dropouts and glitches. The connection was peer-to-peer. FireWire devices could communicate directly with each other without the computer as an intermediary. A FireWire hard drive could send data directly to a FireWire video camera without involving the host computer's processor at all. The connection was hot pluggable. Devices could be connected and disconnected without turning the computer off, a feature that the parallel and serial ports of the era did not offer. And the connection provided power. A FireWire cable could supply bus power to connected devices, eliminating the need for separate power supplies for small peripherals. These capabilities, taken together, represented a substantial technical advance over anything available in 1994. Sony's DV camcorders, introduced in 1995, included FireWire connections and required FireWire to transfer video to a computer at full quality without compression artifacts. The professional video and audio industry adopted FireWire rapidly and enthusiastically because it was the first consumer interface capable of handling their data requirements without compromise. Apple introduced FireWire on the iMac G3 in 1999 and began marketing it aggressively as the technology that made digital video editing accessible to consumers. Steve Jobs called it a 10-year idea, a standard designed to handle the data requirements of devices that didn't yet exist but would within the decade. The assessment was technically accurate. The commercial outcome was not what the assessment implied. The USB consortium that began work in 1994 had a different problem in mind. Intel's representative in the consortium, Ajay Bhatt, who is credited as the primary architect of the USB standard, was not primarily concerned with bandwidth. He was concerned with ease of use and market penetration. The personal computer market in 1994 was massive. Hundreds of millions of PCs were installed worldwide, and the number was growing rapidly. The peripheral market, the printers, scanners, keyboards, mice, and other devices that connected to PCs, was even larger. The technical and experiential barrier that the existing parallel and serial interfaces created was costing the entire industry revenue. Consumers who wanted to add peripherals but found the connection process too complicated were simply not buying peripherals. Butt's design philosophy for USB was subordinate to this commercial reality. USB was not designed to be the fastest possible interface. It was designed to be the easiest possible interface, at a speed adequate for the most common peripheral applications, at a cost low enough to be included on every PC without meaningfully increasing the system price. The original USB 1.0 standard, ratified in 1996, specified a maximum data rate of 12 megabits per second, 30 times slower than FireWire's 400 megabits per second. This was adequate for keyboards, mice, printers, low-resolution scanners, and low-speed storage devices. It was completely inadequate for digital video, high-resolution audio, or professional external storage. But USB 1.0 was not trying to be adequate for those applications. It was trying to be adequate for the peripheral applications that the majority of PC users actually had, delivered with a user experience so simple that the phrase plug and play, which had been used ironically for years to describe the complicated device configuration required by existing interfaces, would finally be literal. A USB device plugged into a USB port worked. Without IRQ configuration, without DMA settings, without turning the computer off. The operating system detected the device, loaded the appropriate driver, and made the device available, typically within seconds of connection. This experience, which seems unremarkable today because it has been universal for 20 years, was genuinely transformative in 1997 and 1998 when USB began appearing on consumer PCs. The consumer who had tried to install a scanner on a Windows 95 PC and spent 2 hours with the parallel port configuration and the IRQ settings and the driver disk experienced USB's plug-and-play as something close to magic. Microsoft's support for USB in Windows 98 was the commercial inflection point. Windows 95's USB support was limited. Windows 98 made USB a first-class interface with comprehensive driver support and a user experience that matched the promise of the standard. The combination of Windows 98 and USB-equipped PCs from the major manufacturers created a market condition in which USB peripherals could be sold to a consumer audience that had no interest in technical specifications and every interest in things that worked easily. The 7-year period from 1998 to 2005 is the period in which the connection war was actually decided, though the decision was not apparent until several years after the critical choices had been made. FireWire held its position in professional and enthusiast markets, where its technical advantages were decisive. The DV video editing market, which Apple had specifically cultivated with iMovie and Final Cut Pro, was entirely FireWire dependent. The professional audio market used FireWire audio interfaces from companies like DigiDesign, Motu, and Focusrite that provided the isochronous transfer and low latency that FireWire's architecture guaranteed, and that USB 1.0 and early USB 2.0 could not reliably deliver. External hard drives were where the commercial dynamics played out most visibly. FireWire external drives were faster than USB 2.0 drives in sustained transfer performance, even after USB 2.0's 480 megabits per second specification was introduced in 2000. The reason was architectural. FireWire's peer-to-peer design and isochronous transfer guaranteed consistent bandwidth, while USB 2.0's shared bus architecture meant that performance varied with the number of devices connected and the behavior of the host controller. But USB 2.0's specification matched FireWire 400's specification on paper, 480 megabits per second versus 400 megabits per second, and marketing materials for USB 2.0 products consistently led with the specification number rather than the real-world performance. The consumer choosing between a FireWire drive and a USB 2.0 drive saw that USB 2.0 was faster on paper and typically chose USB. The consumer was not irrational. The performance difference between FireWire 400 and USB 2.0 in typical consumer use cases, transferring files, backing up documents, storing music, was not significant enough to justify the price premium that FireWire drives typically carried. The consumer who was not doing DV video editing or professional audio recording had no application that exposed the architectural difference between isochronous and asynchronous transfer. The market that FireWire needed to survive, the mass consumer market of external storage and general peripherals, was a market in which its technical advantages were invisible to the buyers it needed to attract. Apple's decision-making about FireWire between 2000 and 2012 is the most consequential factor in the technology's commercial decline, and it is also the most difficult to interpret with confidence. Apple had invested heavily in FireWire, in the standards development, in the marketing, in the professional software ecosystem that depended on it. Apple's iMac G3, iBook, PowerBook, and PowerMac all included FireWire as standard in the 1999 to 2003 period. Apple's professional video editing software, Final Cut Pro, was built around FireWire as the primary video transfer interface. Apple had a clearer commercial interest in FireWire's success than any other computer manufacturer. The 2005 introduction of the iPod Nano and the 2007 introduction of the iPhone began the process that would determine FireWire's fate, though the connection was not immediately apparent. The iPod, originally introduced with FireWire connectivity in 2001, was the consumer electronics product that more than any other established USB as the universal connection standard in the consciousness of the mass market. Apple had included FireWire on early iPods because FireWire's superior transfer speed made syncing large music libraries faster than USB 2.0 allowed. Then Apple eliminated FireWire from the iPod. The stated reason was that the iPod's small form factor was better served by USB's smaller connector. The practical reason was that USB was universal. Every PC in the world had USB ports, while FireWire was standard only on Macs and on a minority of Windows PCs. A FireWire iPod required the PC manufacturer to include a FireWire port, or required the consumer to purchase and install a FireWire card. A USB iPod worked with every PC already sold. The market Apple needed for the iPod to succeed was the Windows PC market, which was 10 times the size of the Mac market. That market ran on USB. The iPod followed the market. The decision was commercially rational. It was also the beginning of the end for FireWire as a mass-market technology. The licensing decision that has been most consistently cited as a factor in FireWire's commercial failure was Apple's decision to charge a licensing fee for FireWire ports. Apple held patents on FireWire technology, specifically on the physical connector and the cable, and charged device manufacturers a licensing fee for including FireWire ports. The fee was reported as approximately $1 per port for device manufacturers who included FireWire ports on PCs and peripheral devices. $1 per port sounds modest. In the context of the PC hardware market, where manufacturers competed on margins measured in single digits and where the bill of materials for a PC was constantly being reduced to maintain price competitiveness, $1 per port for a technology that many consumers could not articulate a need for was a meaningful cost differential. USB was licensed royalty-free. The USB-IF, the USB Implementers Form, made the USB specification available without licensing fees. A manufacturer who included USB ports paid nothing for the specification. A manufacturer who included FireWire ports paid Apple. This asymmetry was not the sole reason for USB's commercial dominance. USB's ease of use and its early momentum in the consumer market were equally important factors. But it was a factor, and it was a factor that Apple controlled directly. Apple could have reduced or eliminated the FireWire licensing fee at any point. It did not. The reasons Apple maintained the licensing fee, despite its effect on FireWire adoption, are not documented in any public record. The speculation that engineers and industry analysts offered at the time ranged from straightforward revenue motivation, the licensing fees were generating meaningful income, to a strategic calculation that FireWire's strength in the professional market was more valuable than its expansion into the mass consumer market, where USB was already dominant. Whatever the reasoning, the effect was to reduce the economic incentive for PC manufacturers to include FireWire ports and to give USB an economic advantage in the mass market that compounded its other advantages.
The professional video market's experience with the transition from FireWire to USB 3.0 illustrates the specific costs of the standard's displacement. FireWire's isochronous transfer guarantee, the feature that delivered data at a consistent rate regardless of other system activity, was not replicated in USB 3.0. USB 3.0's 5 gigabit per second specification was substantially faster than FireWire 800's 800 megabit per second specification, but the underlying transfer architecture remained asynchronous rather than isochronous. For many video applications, this architectural difference became invisible as processing power increased. A modern computer could buffer USB data fast enough that the inconsistency of the transfer rate was smoothed before it reached the application. But for the most demanding real-time applications, live video capture, professional audio recording with very low latency requirements, the architectural difference remained relevant. The professional audio industry addressed the USB architecture's limitations through a combination of driver development and hardware buffering that added cost and complexity to USB audio interfaces. Professional audio interface manufacturers who had built products around FireWire's guaranteed isochronous transfer spent substantial engineering resources developing USB audio implementations that delivered comparable reliability through different means. The result, by the mid-2010s, was a professional audio interface ecosystem in which USB had achieved functional equivalence with FireWire for most professional applications, not through architectural superiority, but through engineering effort that compensated for architectural limitations. This was a real cost. The engineering resources spent developing USB audio drivers and hardware buffers that compensated for USB's architectural limitations were engineering resources not spent on other improvements. The transition from FireWire to USB in the professional audio market was not free. It was expensive in engineering time and in the disruption to users who had to replace working equipment with functionally equivalent but physically incompatible replacements. Marcus Webb's $14,000 in Burbank was a specific instance of a cost that the professional video and audio industries absorbed in aggregate across thousands of facilities and hundreds of thousands of individual users.
Thunderbolt, the interface that Intel developed in collaboration with Apple and that Apple began including on MacBook Pros in 2011, was FireWire's technical successor in the sense that it provided the high-bandwidth, low-latency connection that professional applications required. Thunderbolt's initial specification provided 10 gigabits per second, 12 times FireWire 800's bandwidth, with a physical connector derived from the mini DisplayPort standard. Thunderbolt 3, introduced in 2015, provided 40 gigabits per second over a USB-C connector. Thunderbolt 4, introduced in 2020, maintained the 40 gigabit specification with improved minimum performance guarantees. The professional video and audio communities that had used FireWire adopted Thunderbolt with considerably less friction than the transition to USB had involved. Thunderbolt's performance was sufficient for the most demanding professional applications, and its adoption was fast enough that the installed base of Thunderbolt peripherals was substantial before the professional community was asked to make major equipment replacements. But Thunderbolt repeated the commercial pattern that had limited FireWire. It was a premium interface that commanded premium prices and that achieved mass market adoption slowly relative to USB. The licensing fee for Thunderbolt was higher than for FireWire, and the additional certification requirements for Thunderbolt products added cost to device manufacturers. USB continued to evolve in parallel, USB 3.2, USB 4, with specifications that approached Thunderbolt's performance for common workloads. The consumer market followed USB. The professional market used Thunderbolt for demanding applications and USB for everything else. The pattern established by the FireWire USB competition reproduced itself in the Thunderbolt USB competition with sufficient similarity to suggest that it reflected something fundamental about how connection standards compete, rather than something specific to the technologies involved.
The lesson of the FireWire story is not that better technology always loses. FireWire was not universally superior to USB. It was superior in specific applications and inferior in others, and the applications where it was superior were a smaller market than the applications where USB was adequate. The lesson is about the relationship between technical superiority and commercial success in markets where the consumer cannot directly evaluate technical specifications. The consumer choosing between a FireWire peripheral and a USB peripheral in 2002 was not in a position to evaluate isochronous transfer guarantees or peer-to-peer communication architecture. The consumer was in a position to evaluate price, compatibility, and ease of use, and on all three of these dimensions, USB had advantages that FireWire's technical superiority could not overcome. The professional user who understood the technical specifications and whose applications required the specific capabilities that FireWire provided chose FireWire. The professional market sustained FireWire through the period when USB was establishing its dominance in the consumer market. But the professional market was too small to sustain the semiconductor investment and the manufacturing volume required to keep FireWire competitive as USB's specifications improved. By the time USB 3.0 provided performance adequate for most professional applications, FireWire's ecosystem had shrunk to a point where manufacturers had little incentive to continue investing in it. The cameras stopped including FireWire ports, the computers stopped including FireWire ports, the external drives shifted to USB. The technology did not fail technically. It succeeded technically, in the specific sense that it delivered the performance and reliability that its designers intended for the applications that required it throughout the period of its commercial relevance. It failed commercially for reasons that were partly technical, the licensing fee, the incompatibility with Windows PCs, and partly structural, the smaller market of applications where FireWire's advantages were decisive compared to the larger market where USB's adequacy was sufficient.
Marcus Webb, the video editor in Burbank who had noticed the missing port in January 2009, eventually adapted to the USB and Thunderbolt peripherals that replaced his FireWire equipment. The adaptation took about 6 months, a period of workflow disruption, unexpected incompatibilities, and the frustrating experience of replacing equipment that worked with equipment that also worked, but required everything else to change. He described the adaptation as successful in the sense that his workflow eventually returned to the efficiency it had before the transition. He described it as unnecessary in the sense that the technology he replaced was technically superior to the technology he replaced it with for his specific applications in the specific ways that mattered for his work. The $14,000 was gone. The 6 months of disruption were over. The FireWire ports that had served him well for 11 years were no longer on the machines he was buying. He still had his original FireWire cables in a drawer. He could not explain why he had kept them. He suspected it was the same reason that people kept things that had worked well for them, not because the things were still useful, but because throwing them away felt like acknowledging something that was not entirely comfortable to acknowledge.